Okay, welcome everyone to the 86th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Srikanth Iyengar from the University of Utah, and the title of his talk is The Stable Module Category of a Finite Group is Locally Regular.
Should I stop my video, Rudhadeep, just because I think the internet connection here is a bit dodgy, so I'm not upstairs. Or do you want me to see the video? You can still see my screen, so. Okay, I'll keep it on if you prefer. And then if it...
Yes, please. We need to see you.
All right. I was going to start a pre-recorded talk. Thank. Okay, so please, as I said, please don't hesitate to interrupt with questions in the middle. And also don't hesitate to stop me if I start writing too small or illegibly. Okay, the title of this talk is The Stable Module Category of a Finite Group is Locally Regular. And as I stated in the abstract, the whole point of this, all I want to do is explain what I mean by this statement. And this is, by the way, based on work with long ongoing work with Dave Benson, Henning, and Julia Pevtsova. I think at least Henning is here. And at the moment, the provisional title of our preprint is Local Regularity and Local Dualizability for Modular Representations. I was hoping we would post it before this talk, but that hasn't happened. But I'm optimistic it'll appear soon to be defined. All right. So, I mean, there are two aspects to this. There are two words in this title of the preprint: regularity and dualizability. The project started more than 7 years ago for us in trying to understand what are the local dualizable objects in the stable module category. And we eventually realized not so long ago that the key property that seems to govern, that seems to tell us what is going on is something called local regularity. And this is really what I want to explain. But anyway, let's get started. So the first part, let's take a finite group. And a field of positive characteristic. And I'm talking of modular representation, so I'll assume that G divides the order of the group, and I'm going to assume G is not trivial. So the order of the group is at least P. Okay, and we'll be looking at modular representations, and we'll look at all KG modules, not just the finite dimensional ones. And maybe at some point I need to talk about the finite dimensional representation, so that will be lit mod KG. So these are the finite dimensional KG modules. And the star of the show is mod KG, the stable module category of the finite group. So this is the triangulated category. But what is important for today is also that it is a tensor triangulated category where the tensor product is given by tensor product of K with diagonal G action. So stamod KG is a symmetric monoidal category. That's a TT category. There's a TT category. And the main theorem, and I can state it right away, is that as a TT category, the stamod KG is locally regular. Right. So first of all, I should clarify that here regularity is not sort of the obvious thing. So in the sense, the first thing that might come to mind when you talk about regularity in the context of a ring is global dimension, but let me remind you that under the hypothesis that we are, the global dimension of the group algebra is infinite. So it's not in that sense that it's regular. And the key point here is that it's local, and it's local with respect to the spectrum. Local with here means local, locally on with respect to the action of the cohomology ring of the finite group. So this, is it's always graded commutative, but this is also a Noetherian. So this is a Noetherian graded commutative ring, a finitely generated K algebra. And it's local with respect to the action of this cohomology ring. And as I said, I will clarify what this means. So roughly speaking, the way I'm thinking about this is that although the ring itself, Kg, is not regular, the derived category, the stable module category, this behaves like derived category behaves at least locally like the derived category of a commutative Noetherian regular ring. Noetherian regular ring. And I'll try to, I'll try to flesh out this analogy as we go along. So this is, at least people who have worked on this subject know that the properties of somewhat Kg at least resemble those of a complete intersection ring, but it seems that in some aspects it's actually even like the derived category of a regular ring. And the crucial point is that this aspect, to see this aspect of this category, you need to look at not just the action you have to look at not just you have to look at the stable module category with the action of the cohomology ring thrown in. In some sense, it's not unlike what happens for complete intersections. Not quite the singularity category of a complete intersection, locally complete intersection, behaves like the derived category of a regular ring, but for that you have to throw in the action of the cohomology operator. So in that sense, that's the analogy I want to develop. Okay, so this is what this statement is trying to say. As I said, I will flesh this out as we go along. But the applications, at least for the moment, the key applications for us is that it gives us cohomological criteria for detecting two properties, cohomological criteria. For detecting objects that are locally compact, so detecting compactness, and also dualizability. But locally compact objects that are compact in the local strata of somewhat Kg, and also objects that are dualizable. And this is really where the project started. As I said, this is a bit vague, but I will get back to this. Let me explain. Let me start talking about a model an example that serves as a model for all that comes. And this is maybe also explain some of the points I'm trying to make. So let's start with a case where A is a commutative Noetherian ring. And I want to look at D of A, which is a shorthand for D of mod A, the full derived category of. So one knows that this is a tensor category, compactly generated triangulated category. And the compact objects So by this, I mean the compact objects as the perfect complexes, those that you can build out of A. So these are the perfect, what are called perfect complexes. Okay, so these are the compact objects, and this is even a tensor triangulated category where now the tensor product is given by the derived tensor. Okay. So in fact, this it's sort of not terribly important, but let me mention this, that A is a generator for thinking, just by almost by definition. Okay. So in this context, for each prime P in spec R, a spec of A, for each, if you fix a prime ideal in the spectrum of the ring, there are some functors which are local cohomology functors. D mod A, where gamma P of M, this is, you can take this to be a definition. You look at first localize M at P, and then look at the part of it that's supported on the closed subset V of P. So here, this is the usual localization. And this is local cohomology supported on or the functor that represents local cohomology supported on the closed subset. In fact, because I've already localized, you're just looking at the spectrum of A localized at P, and you can just, maybe this is not, this is. So I'm just looking at what is supported at the prime ideal P. So it's not so important that if you haven't seen this construction before, the key properties are the following. First of all, a gamma P does live only on the prime ideal P, in that the support of this complex is contained in this prime ideal. It will be non-zero if gamma PM is non-zero. And I think one thinks of this, I think of this as the sort of the P local stratum of M. And one justification for that is that you can reconstruct M in the following sense from its P local strata. The localizing subcategory generated by M is the same as that generated by the strata. So this is what is sometimes called the local global principle. Okay, so this is telling me, for instance, that if gamma PM is zero, if these are all zero at this is zero at each prime, then M has to be zero in particular. And then there is a third important property, which is sort of minimality or stratification or minimality, which says that if you take anything which is non-zero in this P local strata of the derived category, then you can generate every other object from here. This is what's called stratification, minimality. Okay, and I should mention here the first two properties. Well, the first properties are not so hard, but anyway, the last one is due to Amnon Niemann. I'm going to be a bit lackadaisical about giving attributions, but this I should mention that this is Amnon's work. Okay, so as I said, I think of these as the P local stratum of the derived category. And what the statements here are telling us is that in some sense, the derived category is built out of its P local stratum. So the message I take away from this is that, when we say some property of the ring is local, I mean that it is something that is captured by its p-local stratum. So a local property, property of A is, yeah, maybe, okay, a local property means something that is captured by the p-local strata. Of course, not every property of a ring is going to be local, but when we say some property is local, this is what I should like to think it means. So now let's get to regularity. So the usual definition of regularity, so A is regular, remember A is a commutative Noetherian ring. This by definition means that the A localized at P, this local ring is regular. Of course, this begs the question, what does this mean? Well, the commutative algebra definition of what it means for a local ring to be regular is that the embedding dimension of AP should be of the local ring should be the dimension of the local. Okay, but of course, I'm trying to understand things in terms of the derived category, but then this is tantamount to the statement that this is tantamount to the result of the global dimension of AP is finite. And this is, of course, Auslander Buchsbaum said. Okay. Now, what does this global dimension of A, what does this statement mean? This is saying that if you look at the bounded derived category of the local ring, then that coincides with the perfect complexer. So this is saying that of course, one always has an inclusion. The thick subcategory generated by A localized at P is contained in the bounded derived category of A localized at P, but global dimension finite is equivalent to, this is now a theorem, this is equivalent to the statement that every such complex is perfect. Okay. But this doesn't, this is a little bit unsatisfactory from the point of view I'm pushing here, namely that this is not really talking about things local to, this is not expressing the regularity in terms of these local strata, because this is looking at all, this is looking at the derived category of A localized at P, which is much bigger than the local strata. The local strata, of course, is contained in this stratum is contained in the derived category, the full derived category of A localized at P, but it's only one piece of this category. And one would like to understand regularity in terms of this stratum. Now, sitting inside this is sort of it's sitting inside this is the image of the compact objects in the big category. So this is C, where C is compact. So C is perfect. I should have written P. Okay. But of course, this is the same as saying you're looking at the thick subcategory generated by the image of the ring itself. Okay. And here's an exercise for you, or if you maybe you've done this already. If you A is regular if and only if this subcategory here that I just introduced has a strong generator. Has a strong generator for all spec A. In fact, one can make a more precise statement that A is regular at P if and only if this subcategory here, this subcategory has a strong generator, but that okay, but that seems to be a special feature of commutative Noetherian rings. So if you want to check regularity, it's enough to check that in each stratum, the image, the subcategory generated by these compact objects, by the image of the compact objects in the big category, this has a strong generator. By the way, by a strong generator, I mean that there is, so what this means, and because A itself is a gamma PA is a generator for this is equivalent to the condition that you can get anything in this category from gamma PA in a certain number of steps using only a finite number of mapping cones. Of course, you allow arbitrary finite sums and retracts, but then you only need a fixed number of mapping cones to get to any object in this category. So I like to, I let you do this as an exercise. And this has, one can also, to try and, maybe I should say one can, here's a consequence that'll come back to later. So there's an application, maybe it's a corollary. If you take something in the P local stratum of A or D of A, then then of course, this one, this is itself a triangulated, this is itself a compactly generated triangulated category in its own right. In fact, it's a TT category. And the tensor product is the usual tensor product of the thing, and the unit object here is gamma PA. So just keep this in mind. And therefore, you can ask, what are the compact objects here? What are the dualizable objects here, etc. So one of the corollaries of this, so one of the corollaries of the regularity condition is that, say, when A is regular, then you can detect, and again, we're looking X in the P local strata of D of A, then X is compact in this P local stratum, if and only if it has finite length. As an A localized P mode. And AX is dualizable in this category. As I said, it's a TT category, so there's a notion of dualizability, and I'll get to that later if you haven't seen this, if and only if H. So the R module, the AP module is Artinian. Is Artinian. So this gives us, as I said, a cohomological way of detecting compactness and dualizability. Maybe let me make a further remark in this context. So in always, what one has is that if you look at the, you fix it, I'm looking at gamma P D of A, and okay, so if you look at the compact objects, we know that this is, so this is something one knows, that the compact objects in this category, in this P local stratum, these are the perfect complexes of AP modules. So this is, you're looking at the perfect complexes of AP modules which have finite length homology. And of course, then this is contained in all AP. So it's certainly contained in everything here in the thick subcategory in such that the length of is finite. So So these are the roughly. So these are the compact objects in the p-local stratum, and these are the ones which have finite length homology. And the regularity condition says that the regularity condition implies that these two are equal. In fact, in this context, equality holds if and only if A is regular at P, so AP is regular, if and only if equality holds. You should think about this. So the quotient of the finite length objects by the compact objects might be thought of as the local analog of the singularity category of A. So this may suggest that we look at this this quotient. So X and dVA, the length of is finite, the modulo of the compact objects. It's some local analog of the singularity category. So, and the regularity condition in this case, I said here that regular implies that this quotient is zero, but in fact, in this in the commutative Noetherian case, it's not so hard to check that it's equivalent to the local singularity category being zero. Okay, and again, the reason I bring this up is that this is truly a local criteria for regularity in that it only depends on the local stratum, the p-local stratum of the derived category. All right, so let me just say one more thing about this model before we move on to the general context. So in talking about the notion of regularity, I've chosen to introduce it by looking at this p-local p-torsion subcategory gamma PDA. But for general A, for any A, so any commutative Noetherian ring A and prime ideal P, there is an equivalence between the thick subcategory generated by the image of the generator and the completion of A localized at P and the thick subcategory generated by the injective hull at P. So this is the injective hull of the residue field at P. So one has an equivalence of categories like this. So this is this is due to Dwyer and Greenlee. So this follows from their work, and this is nothing but classical Matlas duality. Again, it follows from classical Matlas duality. So what this means is that although I've chosen to introduce the regularity condition based on this category, one could just as well have said that the ring is regular if and only if this p-local p-complete stratum has a strong generator of this particular one, not the stratum, but this thick subcategory has a strong generator. And it's tantamount to saying that the thick subcategory generated by the injective hull has a strong generator. There are three different avatars of the regularity property. And sort of what falls out of this is that the regularity property is inherited by completions, because here I'm talking about the P completion of A localized at P. Okay. Now, the next part of this talk is to say that basically to record that everything that I've said so far extends to general TT categories, these constructions and notions. So that's going to be the third part. Any questions so far? All right. So now
a little question, Srikanth.
Yeah, yes.
So the category generated by the injective hull does agree or does not agree with the category generated by the residue field?
It doesn't, right? Because if you look at the residue, the injective hull is an infinite length thing.
Oh,
So yeah, so it's not quite. I'm looking at the thick subcategory. I'm not looking at the localizing.
okay, okay.
Yeah, that's
Right. Thank you.
It's looking at complexes of finite, p-local p-torsion complexes of finite injective dimension. So what this is really saying is that finite global dimension is equivalent to finite sort of injective dimension of these finite length objects. That's what it's saying. Okay. So now let's take T to be any tensor triangulated category. So this is a TT category. And what do I want to assume? So this is compactly generated, just to record everything I want. I'm also going to assume that it is rigid. The global category is rigid. So what this means is that the dualizable objects and compact objects agree. Okay, and I'm going to assume that T is Noetherian. So these are all the examples. Well, the examples I have in mind all have this property. So what this means is that if you look at let's say if you look at the endomorphisms, I mean the full ring of endomorphisms of the unit object, which is always graded commutative, I'm assuming that this is Noetherian. And if you look at, I could have looked at endomorphism of compacts, but let's say if you look at any two compact objects, this is finitely generated. Okay, so I'm looking at Noetherian categories. Yeah, so I wanted compactly generated, I wanted rigid, and I wanted Noetherian. And for simplicity, I'm going to assume that the compacts have a generator, not necessarily a strong generator, just a generator. So, and I ought to be calling the generator G, but since our work is entirely about groups, G would have been a horrible choice, and finding a notation, appropriate notation for this has been a bottleneck to finishing the paper. I'm going to propose calling it a J. J for a generator. So I'm going to assume that this is not terribly important, but it's helpful later on. So I'm going to assume that J is generates the compact object. So the compact objects have a generator. I'm not assuming that it is strongly generated, just that it is generated. Okay. And the key examples to keep in mind, of course, the derived category of a commutative Noetherian ring. In which case, well, I already talked about the tensor product with the unit here. I think I should have mentioned it earlier. This is A, and the endomorphism of the unit is just A itself. And the generator here is also again A. So this falls under this purview of this context. And then the second one, now, unfortunately, the stable module category directly, this doesn't apply directly to the stable module category, but one instead considers the homotopy category of injective Kg modules. So this is again a compactly generated tensor triangulated category. So the tensor product here is again this with the diagonal action. And the unit of this TT category is the injective resolution of K. Okay, and what else should I say? Oh yeah, the compact objects. So the compact objects, all this we know thanks to work of Henning, that this is equivalent to the bounded derived category of finite dimensional Kg modules. Okay, and as I said, the stable module category you get from here by just throwing away the ones which are generated by Kg. So really locally accept at the maximal ideal of the homotopy category and the stable category are equivalent. So this local regularity condition was only talking about things that happen locally, and locally stomod kg is the same as the appropriate localization of the homotopy category. Okay, so that's why I'll be working, one can think of the homotopy category of injectives rather than the stable module category. All right. So anyway, back to the general context. So recall that we have T in 1, and then I said R would be the endomorphism of 1. And just like in the context, like in the case of a derived category, if you look at any prime in the homogeneous spectrum of R, there are these local cohomology functors that go from T to T, and they have similar properties. So the key properties are much the same as what we have before. Of course, I haven't defined what the support is, but one can almost define the support using the local cohomology functors. So these are this is contained in E for all X, and then X in T. And then this is the local global principle that you can reconstruct X from its local pieces. Okay, so these two always hold, but minimality it doesn't follow from the axiom, but it's an additional property that one introduces. So minimality is not for free. Is not for free. Yeah. We have to introduce this, and this is sort of. So what I'm trying to say here is that gamma p of t need not be minimal, but these are the sort of the local pieces of the triangulated category. And if you have minimality, you have some, one can classify the localizing subcategories of the triangulated category and the thick subcategories of the compacts and so on. So anyway, the focus is going to be on understanding T through its local strata, by which I mean the P local, by which I mean this subcategory of T. Okay, so we have this functor gamma P, and one also has the analogous analog of the completion functor, which is a right adjoint. It comes as a right adjoint of gamma P. Okay, so one gets this almost for free. And the analog of Matlis duality here is Brown Common duality. The Brown Common dual. So, which I'm going to write dpx. So this represents the functor that sends x, that sends an object to the following. So you look at x tensor this, and look at then maps into the injective Hull. So this is an R module, and I'm looking at injective Hull. So the Brown Common dual represents this. So maps from here to this is this one. This. And for when T equal to dA, dP is mapping into the injective Hull. Okay, so these are the three functors, the functors that play a key role in this story. And just like in the context of, in the case of the derived category, one can prove, so this is maybe a proposition that thick subcategory generated by, well, I chose a generator, remember? So this is equivalent to the thick subcategory generated by the localization of J at P and the completion, and this is the same as is equivalent to the thick subcategory. Well, it's of the Brown common edge dual of the generator. There's a op here. And the proof of this, so this is again due to, this is really again the Dwyer-Greenlee's argument that one does, an argument analogous to one of Dwyer-Greenlee's. And this equivalence is basically, it comes from a version of Matlis duality that one can prove, one can establish in the context of this general TT categories. So this is something that what is done in the paper. Let me not dwell into where this is coming from. But this is really Matlis coming from Matlis duality for T, or T localized at P. Okay. So with this on hand, I can introduce the notion of regularity. So T, so we say that T is regular, or maybe I should say locally regular, to emphasize that we are talking about a property that is defined locally, means that or T locally regular, as this is a definition. So means that this has a strong generator. It has a generator, namely, of course, it's generated by gamma P of the global generator, but we want this to be a strong. Okay. So this is then our notion of what it means for a triangulated TT category to be locally regular. And given this equivalence, you can of course express local regularity either in terms of the completion of the generator or a Brown common edge dual of the generator. I should have made this comment earlier that for any Noetherian ring, not necessarily commutative. So one of the motivations, of course, is what I've said before. The other motivation for this definition partly comes from this: for any Noetherian ring, then the global dimension of A is finite if and only if the perfect complexes have a strong generator. And then A has to be a strong generator. I should have brought it up earlier when I discussed the commutative Noetherian ring. But anyway, so these are, this is sort of part of the justification for why this is a not unreasonable definition. And as I said, you can also define this in terms of the completions or the Brown common edge duals. And just like in the case of the derived category of the ring, the applications that flow from it concern, so the key consequences is that we get a cohomological criteria for detecting compactness in this category as well as local dualizability. So if you fix now an object in this P local strata of T, then so X is going to be compact if and only if one direction is clear, that the forward direction is clear, it's the reverse direction that's important. If and only if you look at the cohomology, the cohomology of this object, so what can that possibly mean now? You look at maps from the generator into X. Now this is because X is P local, this is going to be an R localized at P module, and this should have finite length. And in the same vein, X will be dualizable if and only if this RP, the RP module is Artinian.
Srikanth, for this last For this last equivalence, don't you need for all P?
Where did I say that? Where? How? Oh,
No, I'm
this
just
is
asking.
for this state definition requires for all P, yeah. But so I'm assuming that T is regular, so not for all P. So I'm fixing an object in the P local P torsion category, and I'm trying to understand what are the compact objects in this category. And this is telling you that if assuming that T is regular, so I should say, maybe I should clarify, assume T is regular, T locally regular. If you have a locally regular TT category, then compactness is tantamount to a finite length in the P local category. And here, dualizability, it's tantamount to this object being Artinian. Okay.
Yeah.
And as I said, the one direction is always, so if you have a dualizable object, they're Artinian, and if you have a compact object, the length is finite. The interesting part is that you have you can detect it homologically, and this fails if the T is not regular, this property can fail. Already it fails for the derived category of commutative rings, but also in the topological context it fails. So this is really the key consequence that we draw from this assumption of regularity property. Okay. And by the way, just as an aside, it also follows that compacts and dualizables coincide precisely when, in particular, every compact is dualizable. So compacts are dualizable in this category, in the P local stratum. So in particular, this P local strata, although we started with a rigid triangular TT category, the P local stratum will not be rigid unless P is minimal. If and only if P is minimal. So minimal in the sense that it's a minimal prime in the spectrum. Okay, so this is one consequence of regularity. That's sort of the main consequence for our work. So I should now maybe let's spend the last few minutes discussing examples. Of course, I already mentioned this. This is locally regular if and only if A is regular in the usual sense, the commutative algebra sense of the word. And that's in fact was a motivation for introducing these definitions. And the key thing is that if you look at K-ing of Kg, the G a finite group as before, then this is actually locally regular. Yeah, this is sort of somehow one of the main theorems of our work. And I have not said anything about, I'm not saying much about how to prove it, but the proof is by reduction to the elementary abelian case, and then doing with the case of elementary abelian groups. And for the elementary abelian, so when for Ke, one knows that one can, so basically one can go from the homotopy category of Ke. So this is something we have used many times by now. That if you look at the homotopy category of E, an elementary abelian group, then this is, there are comparisons to the homotopy category of DG injective modules over an exterior algebra. So where lambda is an exterior algebra on R cop. So this is an exterior algebra, and this is the homotopy category of DG injectives. differential graded DG injective modules. So this is not quite an equivalence, but we have functors, and we have functors that compare. So these are both TT categories, and part of the problem is that these are not TT functors, but that's there is a known finesse for this. And so we have functors that you can go back and forth, and one deduces that this category is locally regular by proving that this category is locally regular. And roughly speaking, this category is locally regular because it's equivalent to the derived category of, so this is the BGG correspondent. This is equivalent to the derived category of the symmetric algebra on the dual. So it's the minus. I realize now I put the R in the wrong place. It's copies. So this is the BGG. And one knows that because this is, and since this is a regular ring, since this is a regular ring, one knows that this is locally regular. From there, one gets that this is locally regular. And then there's a descent. Actually, in this, one of the things we have to do is track ascent and descent of this regularity property along certain types of functors. And this is very closely related to work of Balmer and company on this Wiertzmüller isomorphism. So if you have two TT categories, T and U, and you have functors, and maybe one of them being a monoidal functor, not the other one, and then one can track the descent of regularity from T to U, which sort of generalizes the descent of regularity along maps of finite flat dimensions. So in some sense, this is an example of this is a TT, or we deduce this from a TT version of the descent of the regularity property along maps of finite flat dimensions. And there's also results that tell you that if you can cover your category with regular cover in a suitable sense, your triangulated TT category by regular categories, then regularity descends to the category in question. But these are all sort of the technical things that go into proving that the homotopy category of injectives over a finite group is regular. Okay, but all this will be explained in the manuscript, and I hope this has piqued your interest enough to want to look at it when it finally appears. I'll stop here for questions.
Thank you, Srikanth. Can we all unmute ourselves and give the speaker a very generous round of applause, please? Okay, if you have any questions, you can ask them now.
Could I ask a question?
Yeah, John,
Yeah,
go ahead.
So can you say something about, the Artinian condition? What does that mean? Is that being a localizing subcategory generated by a K or something?
No, because that would be too much, right? Because it would allow infinite sum. So this is a module over a committee. This is, after all, just a module. And I'm asking that it's an Artinian module. Is that what the question was about? This is just a module over a local ring. And I just wanted, it has DCC. So it's a purely module theoretic condition. So again, the point was somehow to be able to detect. I mean, this is in the spirit of your question with Dave. Can you detect compactness by looking at maps from compacts, right? And roughly speaking, so J is compact. So or I could have put a localized, I could have put a J localized at P here, and that would be the compact generator for the local category. So this condition, I think of as saying that X has finite length in the local category, in the P local category. And this is saying X is Artinian in the P local category. And it says that cohomological finiteness or Artinianness translates to this triangular condition of being compact or dualizable. Yeah.
Thanks.
George?
Yes, I just want to ask if you know if there's any general approach or how to compute those gamma functions.
Yeah,
maybe.
Yeah, you can write down these. I mean, I don't know what exactly you're looking for, but there is, there's a lot of literature on this. In the general TT context, you can write down some homotopy colimits that would compute it. I can tell you when I come up the hill. Oh. Yeah, I know that the standard check complex like constructions that compute, or extended check complex like constructions that compute the gammas.
Also, those gammas also exist for sets of those prime ideals, right? So
yeah, right.
Are they somehow irrelevant in this case, or is everything
No,
captured?
because I'm focusing, and because I'm focusing on properties P locally, I'm just looking at one prime at a time. Yeah. So
Any other questions?
There was something on the chat. Did you see already?
Was there? Probably not. No.
Oh no, nothing else.
In your general TT setting, you have this Noetherian condition. I'm guessing if I wanted to replace it with a weakly Noetherian condition, the Balmer spectrum be weakly Noetherian, there will be problems. But
so the thing is, I don't know how to run this, understand. So if you look at the primes in the Balmer spectrum, I don't know how to construct these Brown common-edge duals and think about these Artinian conditions and finite length conditions. So of course, in this case, the Balmer spectrum coincides with the usual spectrum, so it doesn't matter. I guess it's maybe a shortcoming of my training rather than.
I'm sure it's not that.
No.
That
is the natural thing to think about, but yeah. I mean, another question that comes up, I don't know, is, I've introduced this regularity and I was trying to push this point that it's sort of, it's something like the regularity for the commutative ring, but I don't know, for example, how far, knowing just the TT category is locally regular in this sense, how far it is from stratification, for instance. How far is it from making the P-local P-torsion category minimal? One knows that it can't be in that general because the regularity condition is, so there are examples where I don't know that I have examples right away in my mind, but I don't know whether it implies a stratification, for instance. How strong this condition is, the local regularity of the TT category, of a TT category.
Right. Yeah. Even with some of the topological cases, maybe one can look at.
The topological cases actually that you won't have regularity and the obstruction, and the reason is that you don't have these cohomological ways of detecting dualizability. So I think this is what is special about STAMOD.
Yeah. Okay. Any other questions or comments? Anyone? Well, in that case, let us. Sorry.
To see you.
Yeah. Let us all thank Srikanth once again. Okay. We're supposed to have band breaks next week, so hope to see you there.
Bye. Thanks.
Bye. Stop recording.